So I have this photo that we have these dark clouds over our electricity system. Because we have this climate crisis, we have to have the drastic change. So we have to switch from burning fossil fuels to these more renewable, sustainable energy sources. So we have to switch to wind and solar power. The nice thing is that if we look at what are the costs over the whole lifetime for producing electricity by this wind and solar, so it's actually more economically beneficial to use wind and solar. Maybe not in Finland, but globally at least. If you look at the global scale, so at the moment most of the electricity is coming out of burning coal and gas, but this wind and solar, they are growing almost exponentially. So if these trends continue, so in 5 years we are in the same level as gas, and it's growing rapidly, so that looks promising. But this photo actually shows quite well some of the issues here. So on the sunny side we get energy, but then somehow we need to keep the lights on during the night. So we need energy storage. And then also we are producing a lot of cheap energy on the sunny side. So that's a new resource for us to use for chemical industry. So for this green transition, one of the solutions is electrification. So we need energy storage to electrify the energy system and to keep the lights on during the night. But also we have a lot of opportunities in chemical industry. We can make steel with hydrogen, fertilizers, all kinds of things with electricity. So we have a lot of room for new technologies to take advantage of this cheap resource. But we have to do this transformation in very large scale, and we need massive amounts of material for these new processes. So the question is that what options we should use for these new materials. So here I've looked at the periodic table of elements. On the scale we have the production and then the cost. It's on a logarithmic scale. So typically in chemical industry we use these platinum group metals as a catalyst, and then you all have in your pockets you have a battery that has this lithium, cobalt, nickel. These are not very abundant materials. So to do this green transition, I don't believe that we have enough of these materials. So that's why we need to develop the new processes that are taking advantage of these more abundant materials that, like iron, manganese, chromium, and of course also organic compounds, so biomass. That's quite a bit of work to actually discover what kind of materials we should use. So if you think of how we typically develop these materials, so we have some idea, then my student here gets to the lab and does some research. So for example, for batteries for storing wind and solar power, so we typically start with electrochemical experiments and then continue to flow battery experiments. And then based on those results, then we see or get new ideas what to do next, how to improve this system. This is quite slow process. So as an example, I had a master student who we decided that let's look at what we have in the cupboards. We found some chemicals that were made from in Germany from the 1930s. We were not so sure how pure they were, but we decided anyway to test everything that looks interesting. And in this 6 months, we tested, let's say, 20 compounds. So experienced researcher would test, let's say, 100 compounds per year. And this was compounds that we already had in the shelf. So no need to synthesize or purify anything. So if you need to do the synthesis and purification, it takes much longer, of course. So you can maybe get something like 20 new materials per year. So already some 6-7 years ago, we started to think of how can we make this process faster. So we have this fancy quantum chemical calculations that we can do on the supercomputers. So our collaborators developed some calculation protocols to screen large number of molecules to get understanding of what would be the cell voltage of the battery. So here, these 100 compounds that it takes 1 year experimentally to characterize. So here we could get the cell voltage in, let's say, couple of hours. So it's this really can accelerate the process. And now there's this fancy new machine learning that is a lot of new applications coming up and a lot of new ideas there. So this can accelerate this even further. So with this computational data set, we had something like 30,000 molecules. So then we can use this data as a training model for machine learning, and then we can predict what would be redox potentials of or what it would be the battery voltage. And these 100 compounds, so that can be predicted in a couple of seconds. So we really can accelerate this process. Of course, machine learning is only as good as sort of the data that you use for training. So that's a very crucial point. So you have to have very good data that is representative. Here I can give any structure for this model, and then it gives me a number. And if it's not something that the model has been trained on, it's completely rubbish. So you have to be also very careful with that. Also, only some of the properties are easy to predict by this kind of approach. So as an example, in this computational project, we had experimental partners who made some materials for us. Then we tested them, we charged the battery, and then we tried to discharge, and the battery has already died. So stability is very crucial, and this is also difficult to estimate computationally. So here, our approach for this was how can we accelerate this generation of the experimental data? Because then we can have data that we can use for training of these machine learning models and get more faster predictions. So these are some robots that we have in the lab. So we can make this with pipetting robot. We can make samples of let's say almost 100 samples in one go. And then my students this summer they built this electrochemistry robot from a 3D printer. There's some duct tape that you can see that in the photo, but so now we can measure these 100 samples in one go and measure the electrochemical properties and get also comparable data. So this helps us to get more data faster. It's also very interesting to be working on this field now because of all these changes and advantages that are going on. So how is the future looking like? One option is that now that we have quite a bit of data available. So this is our own data from experiments, from computations, a lot of data from the literature. Now we can use this data in machine learning to use this advantage, this machine learning and the AI to actually suggest what are the best options for new data that we can get. Either to improve the machine learning models or either then to give ideas of materials for the real applications. These can be either computational, so this has been already going on for a couple of for some time. But then the new thing is that we can also do this workflow for experimental side. So there's the synthesis robots, and now we can also start to do this robotic characterization. And with this machine learning, we can also optimize that what are the best experiments that we should do to do only those experiments that give us the most information, so we can minimize also the costs, either on the electricity side for the computations or for the reagents and the chemicals. So to conclude, this electrification is going to happen because we have this inexpensive electricity from solar power. And this opens lot of new requirements, but also opportunities for new technologies and new processes for materials and for basically for everything. And the big question is that how can we accelerate the development of these new materials that we need for all of these technologies? And here we can take advantage of this new fancy equipment that we can make in the labs and the supercomputers and so on. And I believe that we can actually answer this challenge for this green transition and provide some solutions with these technologies. Thank you.